Hello everyone, my name is Ritam Goswami and I, along with my partner Subhankar Mazumder, is going to present you with our final BTech final year project presentation, which is based on detection and classification of diabetic retinopathy using machine learning and transformer. This is the overview of our presentation. So now, what is diabetic retinopathy? Diabetic retinopathy is basically an eye disease which is caused due to prolonged high blood sugar level, which ultimately affects the blood vessels of the retina. So to distinguish diabetic retinopathy eye from a normal healthy eye, there are some features which can be seen in an eye fundus image, which are microaneurysms, which are nothing but tiny weak bulges in the retinal blood vessels, hemorrhages, that is the leaking of blood vessels, which can appear as round or linear red patches on the retina, the hard exudates, which are fatty deposits from the leaking blood vessels that accumulate in the retina, and the soft exudates, which are patches of nerve fiber layers caused by the blocked blood vessels. The labeling can be seen from this diagram. So now, the diabetic retinopathy can be divided into 4 classes, that is healthy, mild, moderate, and proliferative. The classes depend on the amount of these features present in the eye. That is, as we can see here, no features means healthy retina. If only microaneurysms occur, if only minimum microaneurysms occur, it can be classified as mild diabetic retinopathy. When hard exudates, hemorrhage, and microaneurysms occurs, it can be termed as moderate diabetic retinopathy. And when neovascularization, that is abnormal growth of blood vessels, and ultimately the leaking of blood, which then flows into the retinal fluid, is known as proliferative diabetic retinopathy, in which it leads to complete blindness or blurry vision. So the motivation behind our work is that diabetic retinopathy is the leading cause of blindness worldwide, and early detection is crucial for preventing vision loss. The development of an efficient algorithm of diabetic retinopathy will help reduce the burden on ophthalmologists, and the use of neural network models for diabetic retinopathy detection can help identify patterns, predict the presence of diabetic retinopathy at an early age, which can lead to better treatment outcomes. So this is the background of our project, that is based on deep learning and neural networks. So deep learning and neural networks gives us several advantages such as automated feature extraction, multi-class classification, which as we have used in our project, we have classified the diabetic retinopathy into multiple classes. Scalability, that is large data sets can be used. Real-time diagnosis, consistency and objectivity, that is CNN models are very consistent. Integration with transformer and continuous learning. So this is some of the literature review that we have researched on during our project. So from the literature review that we have researched on, these are our research gap, which is that most of the works that are found are using just the classical CNN model, which gives very low accuracy. Furthermore, in most of the cases, only one classification architecture has been used, which leads to suboptimal results. And none of the works are found to give any reliable accuracy value with various stages of diabetic retinopathy. So from the research we have done, we have formulated 2 problems, that is comparison of various CNN models to obtain 2 best models with best accuracy for model freedom, and to improve the classification by using 2 CNN models and incorporating the vision transformer or attention mechanism. So this is the database we have used. So for training, we have basically used the Mesido dataset, which contains 1200 eye fundus images, which are divided into 4 classes as mentioned before. But we have used data augmentation to increase the data point to 2000. We have used the IDRID dataset from Kaggle for testing purposes. So these are the objectives, that is to acquire dataset containing fundus images samples of both diabetic retinopathy and normal cases, to determine performance of various neural networks and perform classification using CNN models, choosing the algorithms of the 2 best CNN models for better accuracy, to incorporate attention mechanism for higher accuracy, and to get various severity levels by training and testing the field models. So this is our methodology. So in our first case, this was a methodology, that is the comparison of various CNN models to obtain the two best models. So our first approach was the data preparation. That is, we collected, as I said, we collected the data from Macedo dataset, which is publicly available. It contained 1200 eye fundus images, which were then augmented and pre-processed. The pre-processing was done for better image enhancement, and the augmentation was done for more data points, so that the model could give us better accuracy values. Next, the training of data. The training. We trained the dataset on using five different CNN models. That is VGJ16, Inception V3, Exception, ResNet 50, and DenseNet 1:1, and obtain different parameters such as accuracy, precision, AUC score, sensitivity, etc. Next comes the comparison of the parameters. So from comparing the parameters, we got that Inception V3 and DenseNet 1:1 were the two best models which could be used for model fusion. So this is the methodology of our phase 2. That is the selection of two best CNN models, as we said before. Inception V3 and DenseNet 1:1 was selected according to the best to the accuracy, precision, AUC score values. So next, our next objective was the fusion of two models. That is, we fused them. We extracted the features from both the CNN models. These feature vectors should represent the learned characteristics from the input data. Then these features were fused or concatenated from both the models. Then when the dataset was passed to the fused model, it provided us with better accuracy and precision. Next, the fused model. Next, the fused features were reshaped to an image for the input to the vision transformer, which would give us better accuracy value for classification purposes. So from the papers we have researched, we have found that only 4% of the paper are using fusion mechanism, and only 4% of the people are using fusion mechanism and fusion transformer, as we can see in the graphs given here. So from this, my friend Subhankar Mazumder will continue. Thank you.
So in the first phase of our work, we have gone through some pre-processing techniques. Here is the simple block diagram. Basically, we have done adaptive histogram equalization so that the image can be further processed for classification. These are the results after performing the adaptive histogram equalization and data augmentation. We have done vertical and horizontal flip with 10-degree rotation of each data points. These are the results we have got after the comparison of CNN models. From this table, we can observe that Inception V3 and DenseNet 1:1 has given best results with our dataset with 94 and 89% of accuracy respectively. Here is the entire workflow of our work. At the beginning, we have collected the dataset that we used for pre-processing. Then this pre-processed dataset is used to compare CNN models like VGC16, Inception V3, DenseNet 1:1, ResNet 50, and Exception. After that, two best model is selected for model fusion. In the fusion part, at first we have freeze the top layers for avoiding overfitting. Then features are extracted from these two models, and then in a new layer, concatenation of those features vector is done. At the end part, we converted the vectors into patches of equal size and reshaped them into equal dimension, which is essential for feeding the data into VIT. And then the data is used for classification of diabetic retinopathy into 4 different stages. Now come to the Inception V3. This is the architecture of Inception V3. Inception V3 is a deep convolution neural network that employs a series of inception modules, each containing parallel convolution layers with different filter size and pooling layers to capture diverse features at multiple scales. As the grid size gradually shrinks through the modules, an auxiliary classifier aids training by providing feedback at intermediate stages. Finally, the output is processed through fully connected layer and classified using a softmax activation function, enabling Inception V3 to accurately identify image content. After training, we got an accuracy of 94%. This is the architecture of DenseNet 1-to-1. DenseNet 1-to-1 is a convolutional neural network with densely connected blocks, where each layer receives feature maps from all preceding layers, promoting feature use and strengthening informational flow. After an initial convolution and pooling, the network consists of four dense blocks that extract increasingly complex features, interprets the transition layers, control feature map dimension. Finally, global average pooling aggregates the feature and a softmax layer makes the prediction. This architecture enables DenseNet 1-to-1 to achieve high accuracy while remaining computational efficient. Here is an result after the training. In this slide, it is mentioned that after the training of DenseNet 1-to-1, we got an accuracy of 89%. Here is the result after the fusion of Inception V3 and DenseNet 1-to-1. So here we can notice that the loss is very high. To minimize this loss, we can use transformers. This is the architecture of Vision Transformer. VIT has revolutionized image classification by treating images like sentences. We use it to break down an image into fixed size patches, much like words, and then transform these patches into a sequence of numerical representation. Just as a sentence has a special word to indicate its meaning, VIT adds a learnable class embedding to represent the entire image. To give the model a sense of spatial awareness, positional encoding are also incorporated. This sequence now resembles a sentence of visual words, is then fed into a series of transformer encoder blocks, which use self-attention to analyze the relationship between different patches. Finally, the class embedding enriched with contextual information from the entire image is processed by a small neural network to output the predicted class probabilities. This is the complete architecture of our new model, which is a fusion of Inception V3, TenseNet 1-to-1, and incorporated with VIT Vision Transformer. It processes the input image through Inception V3 and TenseNet 1-to-1 paths parallelly, extracting diverse multi-scale features. These features are then combined and fed into a VIT, which incorporates positional encodings and multi-head attention mechanism to capture global context and relationships within the image. The final prediction is a result of this sophisticated integration, which is done by hyperbolic tangent activation function before being projected it into the final prediction space using a linear layer, leveraging the strength of both convolutional and transformer architecture for superior image analysis. In this slide, it is shown that the result we got from our final model. Here we can see that the loss is minimized to 25% from 41%, and the accuracy is also increased from 94 to 95%. This is one of the output that our model predicts. It predicted the class correctly with a probability of 94%. So now, for conclusion, we can conclude that by using the VIT, the loss from fused CNN model gets reduced to 25% and the accuracy of the entire model also increased to 95%. This is the Gantt chart of our project. And these are some of the major references that we have gone through to complete our work.
Good morning. So this is our code which helps in classifying diabetic retinopathy into four classes using a combination of Inception V3, DenseNet 1-to-1 and incorporating the Vision Transformer. So this is the model summary of our combined model which combines Inception V3, uh, DenseNet 1-to-1 and the Vision Transformer as you can see here. So this code has been run on a course of 50 epochs. Uh, which has the maximum validation accuracy of 92.50%. This can be increased by increasing the data points or by any hyperparameter tuning. So now let us try to predict predict an image into check in which class it belongs. So let us copy from a different data set. Copy a mild image, as you can see here. Here's the code here, part here. Try to predict the image. So yeah, it correctly specifies it as mild with a probability of 93%. So now let us try to predict an image from here. Yes, so it belongs to the healthy class. Here's the part here. It correctly predicts the class as healthy with a probability of 92%. Now let us try to see an image from the different dataset. Uh, Suppose we want to see the image from the validation dataset here. Let us try to no, this time let us try to take a moderate image. So yes, it correctly specifies the class as moderate with a probability of 94%. For a severe image, again our model correctly specifies the class as severe with a probability of 94% this time. Thank you.